Today we're carrying on with our surd theme. Why use surds? Well, if you remember back to when we were doing Pythagoras, we were getting our answers in square root form. So if we had a 3, 4, 5 triangle, we knew that 3 squared plus 4 squared was equal to 5 squared, and we needed to find the square root to find our side. So the square root of 5 squared is 5. That's a nice whole number. But sometimes the number you get when you square root your answer is a horrible decimal, and it can be rounded, which introduces errors. So surds are a nice way of showing a perfect answer. And if you're doing multiple sums, multiple triangles, a surd answer stops you having to work out the in-between decimal. It also reduces the chance of you introducing errors into your actual answer. So today we're going to be looking at rationalising the denominator. Now that's a lot of words with a lot of scary thought involved, but it's not actually a hard thing to do. So if you remember, denominators are to do with the bottom of a fraction. So what we have, apart from the wrong lid on the pen, is a fraction but with a surd on the bottom. So for example, 2 root 5. We don't like having numbers on the bottom of a fraction that are not whole numbers. And root 5 is not a whole number. So when we get this sort of case, we use what we know about fractions and their equivalents to get us a whole number answer. What I'm going to do is times top and bottom by root 5, because root 5 times root 5 is 5. This is where all our maths knowledge so far starts to come together. So we know that root 5 times root 5, you times across when you're dealing with fractions, so we have 5. But on the top we've got 2 times root 5, so we've got 2 root 5. We've not got rid of the surd, we've just moved it into a place where it's useful. I'll give you another example. If I have root 3, 3 root 2, now in this case I have two options. I can multiply by 3 root 2, or I can multiply just by the root 2, because the 3 is already a whole number. So I'm going to choose the second option, because it's slightly less work. And what we get on the bottom there is 3 times root 2 times root 2, which is 2. And on the top, we have root 3 times root 2. And if we tidy it up, we end up with root 6 on the top and 6 on the bottom. That was coincidence. Let's try another one. 4 root 6. I'm going to times the top by root 6, and the bottom by root 6, and I'll get 4 root 6 over 6. I'm going to give you an exam question. This is an old exam question from back in the standard grades. And it says to simplify root 2 times root 18 and also to simplify root 2 plus root 18. So what we have here on the top, 18 is 9 times 2. So we've got root 2 times, 2 and 9. So here we've got a pair, so that's 2. Root 9 is 3. So what I've got is 2 times 3. 2 times 3 is 6. That's a nice whole number. And here I've got root 2 plus, and we know that 18 is 2 times 9. We know that root 9 is 3. So what I've got is root 2 plus 3 root 2. So I've got 4 lots of root 2. We're then asked to show that 2 times root 2 times root 18 over root 2 plus root 18 equals 3 root 2 over 4. Now when they ask you to show that something equals something, start with one side and see where it leads you to. And by showing each step, you're proving their answer. So I know that the top 2 root 18 is 6. And I know that the bottom root 2 plus root 18 is 4 root 2. So what we need to do is, as we did up here, is get rid of this denominator, this root 2 here. So we've got 6 over 4 root 2 times root 2 over root 2. So we've got 6 root 2 over 4 times 2. What I've got here is even top and bottom numbers. So rather than multiply that up to 8, I'm actually just going to cancel down right now. Oops. So I'm going to cancel that 2 with this 6. And that gets that 6 down to a 3. So what I've got here is 3 root 2 over 4 as required. QED is used to mean and therefore proven. There is a Latin phrase that goes with it, but it escapes me right now. And that's rationalising the denominator.